The ManagerTower Vision Language Model architecture aggregates insights from pre-trained Uni-Modal experts at different levels, enhancing cross-modal alignment and fusion. Unlike previous two tower models, ManagerTower introduces managers in each cross-modal layer to adaptively aggregate Uni-Modal semantic knowledge. This architecture addresses limitations of BridgeTower, including ineffective layer-by-layer utilization and limited scalability. ManagerTower achieves superior performances on VQAv2 and Flickr 30K datasets, outperforming previous strong baselines. The model utilizes the transformer encoder with co-attention, computing output representations using multi-head self-attention, multi-head cross-attention, and feedforward blocks. The proposed static aggregation of Uni-Modal experts, SAUE, manager focuses on aggregating insights of pre-trained Uni-Modal experts, resulting in significant performance improvements. Despite limitations, the adaptive aggregation of Uni-Modal experts manager further improves performance by adapting to input tokens and samples. ManagerTower offers a novel and effective approach to VL representation learning, demonstrating superior performance and scalability compared to previous models. ManagerTower introduces a novel architecture for adaptive aggregation of multi-layer Uni-Modal semantic knowledge in visual language processing, enhancing cross-modal representation learning. This model surpasses many base-size models pre-trained on 4M data and even outperforms some models pre-trained on more data or with larger size. The model's managers are designed to adaptively aggregate more accurate Uni-Modal semantic knowledge to facilitate comprehensive cross-modal alignment and fusion in each cross-modal layer. The adaptive aggregation of Uni-Modal experts, AAUE, manager adapts to different levels of Uni-Modal semantic knowledge from pre-trained Uni-Modal experts for different tokens in different samples. This is achieved through cross-attention and softmax functions to generate adaptive aggregation weights. AAUE managers outperform static sentence-level managers and layer-by-layer exploitation in BridgeTower, as demonstrated by experimental results on VQAv2 and Flickr 30K datasets. ManagerTower consistently outperforms BridgeTower with different numbers of cross-modal layers and Uni-Modal representations, demonstrating its flexibility and effectiveness in adapting to different scenarios. Visualization of aggregation weights for textual and visual AAUE managers in each cross-modal layer after VLP demonstrates that the introduced managers can adaptively generate different aggregation weights for different tokens in different samples. Comparative analysis with BridgeTower and ManagerTower with SAUE managers reveals that AAUE managers achieve significant performance gains due to their ability to adapt and generate different aggregation weights for different tokens in different samples. This highlights the importance of adaptive token-level aggregation in improving cross-modal fusion performance. ManagerTower, a novel vision language model architecture, introduces the concept of managers in each cross-modal layer to adaptively aggregate and fuse multi-layer pre-trained Uni-Modal representations. This approach enhances cross-modal alignment and fusion, improving performance on various downstream vision language tasks. The proposed managers, including Single Attention Unit Expert, Adaptive Attention Unit Expert, and Adaptive Average Unit Expert, effectively combine insights from pre-trained Uni-Modal experts at different levels. The Adaptive Attention Unit Expert manager shows significant performance improvement, albeit with a slightly increased computational budget, highlighting the need for further optimization of other manager types and analysis for better performance with lower computational costs. The study references related work in vision language models, multi-layer representation aggregation, and image recognition at scale, emphasizing the importance of understanding language structure and BERT's role in learning this structure. The paper also discusses scaling up visual and vision language representation learning with noisy text supervision, deep visual semantic alignments for generating image descriptions, and large-scale adversarial training for vision and language representation learning. The development of a unified vision language pre-training model, VLBERT, aims to bridge the gap between vision and language tasks by learning a shared representation space. This is achieved through a novel multi-layered transformer-based architecture that integrates visual and linguistic inputs, enabling the model to perform well on various vision and vision language tasks. VLBERT uses a multi-layered transformer architecture with a novel fusion layer to combine visual and linguistic inputs, pre-trained on a large dataset of image-text pairs using a masked language modeling objective and an image-text alignment objective. The authors demonstrate VLBERT's effectiveness on several benchmarks, including visual question answering, image captioning, and visual grounding tasks. The research paper presents a vision language pre-training (VLP) approach focusing on the implementation details and fine-tuning strategies for downstream tasks. It employs two objectives: masked language modeling (MLM) and image-text matching (ITM). The authors use 4 public image caption datasets for pre-training and a fine-tuning strategy involving standard settings and splits for all datasets. They also visualize the aggregation weights of textual and visual managers in each cross-modal layer, showing the effectiveness of the ManagerTower architecture. The results demonstrate a significant performance improvement of the ManagerTower model compared to the baseline BridgeTower model, achieving the best score on several downstream vision language tasks. The paper concludes by emphasizing the significance of the proposed ManagerTower architecture in achieving state-of-the-art performance. The hyperparameters ManagerTower is configured with 6 layers, a hidden size of 768, and an FFN inner hidden size of 3072. It employs 12 attention heads, a dropout ratio of 0.1, and attention dropout of 0.1. The total steps for pre-training are set to 100,000, with a batch size of 4096 and an optimizer of AtomW. The learning rate is initialized at 1E5 with a linear decay, and a weight decay of 0.01 is applied. Warm-up steps are set to 10,000, and the Atom Optimizer's hyperparameters are set to E equals 1E8, beta 1 equals 0.9, and beta 2 equals 0.98. Center crop augmentation is enabled, while random resized crop, random augmentation, and random horizontal flipping are disabled. The textual encoder is based on Roberta base, and the visual encoder is clip VITB 224/16 with a patch size of 16. The image resolution for visual language pre-training is set to 288. For fine-tuning on various downstream visual language tasks, the hyperparameters are adjusted accordingly. The total epochs, batch size, optimizer, learning rate, and learning rate decay are task-specific, as shown in Table 9. Weight decay, warm-up ratio, and Atom Optimizer's hyperparameters are also task-dependent. Center crop augmentation is disabled, while random resized crop, random augmentation, and random horizontal flipping are enabled for all tasks. The textual and visual encoders remain the same as in pre-training, with the image resolution for fine-tuning set to 576, 384, 384, and 384 for VQAv2, SNLIVE, NLVR2, and Flickr 30K, respectively. The loss function used is either binary cross-entropy or cross-entropy, depending on the task.